Picture this. You wake up in a jungle with no memory of how you got there. You don't recognize your surroundings or neighbors, and there's no clear direction of where you could go. This can be a powerful analogy for how a cancer cell begins its journey in the human body. When normal, healthy cells become cancerous, it's as if they forget that they're part of a tissue and start acting as solo agents. This process of forgetting is complex and can be driven by environmental factors like smoking or radiation, or more intrinsic factors like aging or having certain genetic mutations. But ultimately, forgetting involves the breakdown of a cell's ability to listen and react appropriately to both internal checks and balances and external cues from its environment and neighbors. Instead of communicating and working with surrounding healthy cells, a cancer cell finds itself competing for resources and transforming the environment around itself to survive. Like a lost traveler, a cancer cell can be vulnerable to its environment. It's these vulnerabilities that researchers are hoping to take advantage of to stop a cancer from spreading or metastasizing. In most cancers, a patient's prognosis is dramatically improved when the cancer is caught early, before it establishes another tumor site away from the original tumor. With the help of our lost traveler, we will see how a cancer cell develops a primary tumor site and the different points of therapeutic intervention available to prevent the successful establishment of their base camp. Our lost traveler will have to set up ways to meet their basic needs. For starters, the lost traveler may want to build some sort of physical shelter to protect themselves from the outside elements and to store resources it may gather. Cancer cells must do the same. However, instead of jungle, their surroundings consist of extracellular matrix, such as the proteins collagen or fibronectin, and stromal cells like fibroblasts, which give structure and architecture to the tissues in the body. While cancer cells can manipulate their physical environment themselves, what they really rely on is convincing surrounding healthy cells to do the work for them. Cancer-associated fibroblasts are healthy fibroblasts that have been transformed by neighboring cancer cells to remodel the physical environment by breaking down the surrounding tissue, secreting more proteins, and even cross-linking surrounding proteins to make an environment that will help the cancer cells grow and keep nutrients. In addition to remodeling the environment, transformed cells will even begin to produce and release nutrients like sugar, lipids, and growth factors. Our lost traveler will also have to come up with a way to get water. Early on, they may make frequent trips to a nearby river, but it would be more efficient to reroute some of the water from the river to their base camp. Oxygen is like water for our cancer cells. Every cell in our body needs oxygen in order to generate molecules required for basic cellular maintenance, growth, and motility. Because they're competing with surrounding cells and proliferating at such a fast rate, cancer cells will secrete certain proteins into their environment to call in endothelial cells to build blood vessels throughout the tumor through a process called angiogenesis, which allows them to easily access key nutrients such as oxygen. All these changes our lost traveler has made to set up Basecamp haven't gone unnoticed by the surrounding environment. Our lost traveler now must take measures to protect its base camp and itself from predators. One way that our lost traveler can do this is by bolstering the defenses of their base camp to keep predators out, or it can also camouflage its base camp to hide in plain sight. For cancer cells, the predator would be our own body's immune system. In order to protect itself from immune cells, such as T cells, cancer cells can remodel the surrounding matrix to make it so dense that immune cells can't access cancer cells within. Similar to the way cancer cells can transform neighboring healthy stromal cells, cancer cells can also tell immune cells to quiet down and suppress their ability to attack. In these early stages, both our lost traveler and the cancer cells are adapting to and changing their local environment to survive. One of the main therapeutic strategies that cancer researchers and physicians are investigating is interfering with the communication between cancer cells and the neighboring cells to slow or stop all these changes. These therapies can come in the form of stopping the transformation of healthy fibroblasts to cancer-associated fibroblasts, breaking up the extracellular matrix so that immune cells can get through more easily, and even promoting the blood vessel formation so we can improve the delivery of drugs. Another therapeutic strategy is to interrupt the cancer cell's ability to use any nutrients that the tumor microenvironment might provide. These drugs are known as metabolic inhibitors, and they can interrupt the uptake and processing of molecules such as glucose, lipids, or amino acids for energy to essentially starve cancer cells. Lastly, checkpoint inhibitors are a powerful therapy that help immune cells fight cancer. While therapies which help to break up the extracellular matrix and improve blood flow to the tumor help get more immune cells to the tumor, checkpoint inhibitors can override the cancer cell's attempt to suppress an immune response and reactivate immune cells to kill cancer cells. All these interventions are aimed at compromising the cancer's base camp. By preventing the establishment of this base camp, we could prevent damaging healthy tissues alongside the development of a primary tumor. With this, we can hopefully prevent the lost traveler from setting up the next site.
To continue learning more about the world around you, check out our previous SiteTunes videos. You can also stay tuned about our upcoming projects by following us on Facebook, Instagram, and Twitter.